And you said you'll meet me on Tuesday, right? What happened? Yeah. For grading? Yeah. Yeah, let's meet today. Yeah. Oh, it looks different. I thought that was a whiteboard. When you put the camera on that side, it looks different. Oh, hello, Niranjan.
Good morning.
Email about yesterday. Yeah, I need to.
Huh?
I'll write an email about yesterday.
Oh, it's okay.
You are using net. And we moved to the center, right? Something like that. What was the? Oh, that's here, right? Yeah. That's right. Line. So there's a homework. Homework. So 2 weeks from today, we have the final exam. Oh, not final exam, sorry, midterm on exam. Sorry about that. Yeah.
The midterm will be on 22nd or the Monday after.
Huh? Midterm is 29, right?
Oh, the. So you're from the.
Oh, everything that we cover before 29.
Even the Monday.
I think so. I don't know when the homework will be due and because things get postponed here and there. But by default, everything that's covered before 29, that's a good way to provide. At least that's how I go usually. If there is a clear-cut demarcation and there is something that is entirely different, then I make a different rule. But by default, everything that is covered before 29. How was the homework, latest homework? Or how is it going? Probably it is due at the evening, right?
It's still going.
Still going. It started?
Yeah. I'm done with one question and I'm working on the second.
Okay.
We have to do two of them, right?
I think so.
Question
Yeah.
3 and 4th.
Yeah.
Right?
Yeah. I don't remember. Honestly. Oh, I have
The one that shows points, right? Let's say it's 20 points.
So
There was a confusion or something.
problems 1 and 4 or 2 and 4?
Can you see 2 and 3? 2 seems to be like an example to me.
Oh no, that doesn't matter.
Okay. So
Yeah,
we have to
I think
2 and 3, not
2
4.
and 3. Yeah.
Oh, okay.
I think that's because last time I had made the other problems
Okay.
available.
Oh.
So don't go by the points.
Okay, then
Yeah, good point.
2 is good. I think.
2 and 3.
You
already did 2?
No. I'm about to work on 4th one. I finished 3rd.
One. That's for practice.
Okay.
You gain extra practice. Sorry, yeah.
No, that's
My
fine.
bad. Hopefully it won't hurt too much.
I thought there was a mistake in the heading because the points were written with 3 and 4.
Yeah.
It's okay.
I
That's
should
fine.
be more
Yeah.
careful.
Oh, thank you.
Yeah. Definitely. You cannot complain too much against me, right? So I get a upper hand here. Yeah. Hopefully, yeah. Anything else other than that? So it's going okay. The systematics is clear. What's happening? That is the only main idea that you should get. You should know what you're doing. If you're completely lost, that's dangerous. Then it's something to worry about. But if you know what you're doing, small mistakes, that's okay. Then that can be fixed. You know what? Okay. Nathan is not here. It's okay. Did you get the mailbox fixed? So now you have a mailbox. Okay, so now I can start putting that. Last quiz also, I have it on my table. Yeah, okay. Comments?
No.
Okay, so let's in 2 minutes capture whatever we did and what is the important pieces we want to take from here on, at least for the next 2 weeks. And in principle, I would say, and most of what we do, even in Green's function, because all this has a nice way of building a Green's function, but probably I won't be able to go into that because I might do the standard stuff. But it is well known that all this can be used to build Green's function also. It gets more abstract and it is not very convenient. It may not be, or I usually don't do it. It is easy, but at the same time, it's too abstract. Okay, so the idea is if you have a basis vector, so there are basis vectors, that also is a summary of whatever we did. Right, that is I, and that is and so you call it the covariant basis and contravariant basis, or the tangent vectors, normal vectors, covariant, contravariant, or what are the other names? Downstairs and upstairs. That's simple. That's not technical. Then we have completeness. And that is I. That's equal to 1. Remember, I is sum here. So in principle, there are 1, 2, 3, 4 indices. That 2 of them are written as vectors. And since I is summed up, that's a dummy variable. So independently, there are 2 of them, and that's the 2 vectors that we. That is orthonormality. And that tells you that typically, this is just I started with J. Doesn't matter what is up, down. In very special circumstances that doesn't matter, but in our cases it will not. Again, there are 4. There is 1 vector, 2 second vector, I and J, 4 of them. But this time the vector is contracted. There is a dot product in here, so the vector goes away. What is independent is I and J, and that's your orthogonality. So that's what we want to take home from this point on. And now we have to ask, how do we build these things in simple rectangular coordinates that's already given to us? We are used to using it, rectangular coordinates, spherical coordinates, cylindrical coordinates. But often in many places, you're in a completely new vector space, let's say, or new basis. And how do you have a simple way of easily constructing these eigenvectors? And for that, we take a detour, and this is how we switch to quantum mechanics now. So I'm going to do entirely different thing, is a matrix, simple matrices, and I'll show that every time you have a matrix, we will state a 2 by 2 matrix, 3 by 3 is just extension of that. we'll mostly do everything that we do in the next 2 weeks or maybe 1 week, 1.5 week. For 2 by 2 matrices, and we will see that the eigenvectors of 2 by 2 matrices are this complete set of vectors. That's the simple idea we are going to use. And once we have those matrices, then it's just a matter of can we interpret that matrix in some form. And that is where the quantum mechanics will come in. You will say that, oh, this is an operator. Its eigenvectors have some meaning. What does it mean to measure something? So those are simple interpretations we'll make, but profound interpretations. The consequences will be profound, but otherwise straightforward in many ways. So let's talk about matrices. So the idea is, where do we get our EIs? What is a simple way of doing it? Most of the time, quantum mechanics is done in differential operators, like momentum is usually derivative, right? And energy is derivative in time, momentum is derivative in position. Derivative is an operator that operates on a function. Matrices operate on vectors. So we are going to be using matrices, the simplest form, but ideas will be exactly the same. And here we will be able to separate out the quantum effects much more nicely than the differential operators. Differential operators has this feature that it has a whole of Newtonian mechanics inbuilt in it. So often we are dealing with Newtonian mechanics and it's harder to separate out the quantum effect. So here it will be much more nice, but I'll at least point out 1 or 2 very non-trivial quantum effects, and from there we'll move on. Okay, so here much simpler. We're just talking about matrices, 2 by 2 matrices. Let's pick a simple matrix. You can take any matrix. Typically, when you're doing matrices and eigenvalues, you pick numbers. So here I'll pick vectors just to make it a little sophisticated. It's a 500 level plus, and we're doing eigenvalues, eigenvectors, which most of us probably are all aware. So I'll just put a variable in it, and the idea will be anyway standard, and we'll go through that. So that's a matrix A. We can use double vector for that if you want, but for now, let me just use a simple matrix. So sine theta minus sine theta, and cosine theta. If I restrict my angle theta to 0 and 2 pi, what does this matrix represent? Is this a familiar matrix?
Transformation.
Transformation matrix, and it is a rotation transformation, right? It rotates if you have a 2-dimensional space, this rotates. If it is an XY plane, it rotates one vector whenever you change the coordinate system by an angle theta. That's how a vector will change. But there are active rotations and passive rotations, which we won't need it as of now. Whenever we need it, I will come back and talk about it. So, okay. So that's your matrices, and we would like to talk about a situation where I have a matrix A, and it has to act on something. So let's say a vector X. So a matrix, let's say X is equal to, let's say yeah, Z1 and Z2. Maybe I should say Z. Okay. I changed X to Z because this could be complex numbers. Just by changing it to Z, it doesn't make it complex. I tell that Z allows complex values. So everything in here, we will leave it give it the room that it can be complex. So Z could be complex. Could be complex. And that leads to the issue that I haven't done complex analysis here yet. I postponed it a little bit. So, but the assumption is that to a certain extent, you all have seen complex numbers with the graduate level course, and that is all that I have. And the question is, if I multiply a matrix by a column vector, the matrix multiplication is understood. It's applying on a vector. Can I have a situation where it gives you back my z and a number? So lambda is the number. A complex number. Could be a complex number, real numbers are part of it. And A is a matrix. Okay, 2 by 2. That's a simple question you ask, and that's called the eigenvalue equation. And then you say that, okay, that means that the sine theta minus sine theta, the sine theta, we are asking z1 times z2 equal to lambda times c1 times c2. So I say this is lambda times c1 cube. That's equal to, I can put in a 1 here in between and then multiply out that 1. That's also the same as lambda 0, 0, lambda times z1 times z2. Pull this to the left hand side, subtract the 2, and then I have an equation. The sine theta minus lambda sine theta minus sine theta. The sine theta minus lambda minus z1 and z2 equal to 0. Then moved it to the left hand side. That is all that I did. That is like multiplying a matrix times something, giving you a 0, and then the question is, what are the possibilities, right? Maybe if you have f times c equal to 0, doesn't necessarily mean matrix or anything. Just 2 variables, f and z. I can tell you. What does it mean? If multiplication of 2 quantities gives you 0, either f has to be 0 or z has to be 0, right? One of them has to be 0. So f equal to 0 or z equal to 0, or both can be 0, but at least one of them has to be 0. If you have z equal to 0, that's what is called a trivial solution, in the sense that we are asking the question as to a multiplied by what quantity will give you something multiplied by that same quantity. Of course, 0 multiplied by anything is 0. So this z equal to 0 satisfies the question that we are asking. But that's a trivial solution. If I ask you, 3 multiplied by what gives you something, that might be a trivial. I mean, some special condition makes it go away. And that's what we're talking about. So this is sort of a trivial solution in the way we have asked our question. This is trivial. We are not interested in that, but that's a solution nevertheless. Right? And typically, these trivial solutions have a way of leading to non-trivial stuff, because we always forget that, oh, there was a trivial solution. We never bother to do that. But that is always there. But here, that's not the case. We are interested in the case f is equal to 0. So now f is a matrix. What does it mean to say that f is equal to 0? Right, something has to be 0, and that to a non-trivial solution. In this case, what it means is that the determinant of this has to be a 0. Basically, what it means is that if I were to take this as an inverse, that should be allowed. And overall, what we're saying is that the determinant of f has to be equal to 0. So this equal to 0 immediately means that I'm saying this implies that non-trivial solution for this is that the determinant of the sine theta minus lambda sine theta and I ask you guys to explore this a bit, because this is not as straightforward as I said. why does this equal to 0 imply determinant of this is equal to 0? Like this is an equation, this is a linear set of solution equations, right? So for example, let's say ax plus z1, right? Or a z1, this would be a b c d times z1 times z2 is equal to 0. This is linear set of equations. So c times z1 plus b times z2 is equal to 0. And if this is not equal to 0, typically there are good solutions, there are unique solutions in there. But then if you say that is right side is equal to 0, what does that mean? So tell me why this implies determinant of a, b, c, d is equal to 0. I think about why is that the case. And look up your linear algebra courses and ask why is that equal to 0. That's your quiz. It takes a few more steps of argument to conclude that. Okay. But we are saying this is equal to 0. So what does that mean? So we have this multiplied by this, minus of that has to be equal to 0. So I should be able to go here, I suppose. So I have cosine theta minus lambda, diagonal elements are the same, that's equal to 0, plus sine square theta equal to 0. Oh, this can work. Oh. For now it is equal like this, but I will be going with that. Maybe goes from here. Okay. Oh, again there's one. Oh, but that's the same one.
Yeah.
Try not to go through that. Okay. This is cosine square theta minus 2 lambda cosine theta plus lambda square plus sine square theta is equal to 0. Makes sense. Is it something wrong?
Did you go for last?
Last one?
Before
This one?
no, the first one.
Oh, I did this, right? This multiplied by this. Minus of minus becomes plus, what? Determinant of this?
Yeah, it's
I think it's okay. Yeah. So cosine square theta cosine square theta is 1. So lambda squared minus 2 lambda cosine theta plus 1 is equal to 0. So that's it. Apparently a quadratic equation. We should be able to solve that. So let's solve that. So lambda is equal to minus, right? So it is 2 times lambda cosine, no lambda, right? 2 times cosine theta. So 2 times sine theta plus or minus and square that again. So it is 4 cosine square theta and then minus 1, I suppose. And minus 4. Minus 4 divided by 2 times a, which is 2, right? So this 2 cancels out the everything, all the numbers in the numerator. So that's equal to cosine theta plus or minus. Cosine square theta minus 1 is minus sine square theta, which is the same as plus or minus I sine theta. And that's nothing but in terms of exponential e raised to of or minus I theta. Right. Prove this with I'm pretty sure the quiz you will use something or the other, but try to do it as basic as possible. But that's your call. So what do you mean by basic? Right? So, like the first time this was done, this was a big realization. So, but at that time the input was very less, or complex numbers that went along with it. Okay, so that's your two eigenvalues, plus e raised to plus I theta and e raised to minus I theta. Notice these are complex numbers, right? By construction, they're complex numbers. There's an I showing up explicitly, and that's the eigenvalues. So these are called eigenvalues, right? So eigenvalues, right? Values. And e raised to plus I theta and e raised to minus I theta. Come on. That's this quantity in here. So what that means is that there exists at least one lambda for which when you multiply this a with z, it gives you lambda. You can verify this. Yeah, why not verify it? Yeah, let's verify that. So a times this lambda if you want, a times z is equal to lambda times z. So cosine theta sine, but we need the z, right? Only then we can do that. But not there yet. Do some more work. So first, let's ask. Okay, we found this lambda now. What is the z corresponding to that? That is a particular z that when you multiply the a with, you get a lambda. Is that clear? And how many z's will there be? Two of them, yeah, but I'm saying, is it unique? One would expect there is a uniqueness, but is it really unique? I mean, based on your, have you done matrix like eigenvalues and eigenvectors? All of you should have done this, right? Like eigenvalues, and so what is the meaning of an eigenvector? In this case, this came out to be a complex number, but sometimes, most of the times, you have easier examples when there are real eigenvalues and real eigenvectors also. And if they're real eigenvectors, it's a two-dimensional space, then that's a vector, two vectors, right? So is there a unique vector which gives you this? Okay, so we'll get to that answer as we proceed. Okay, answer is no, it is a whole line of points. Okay, so, or actually you can see this, right? If z is a solution, if z is an eigenvector. Right, let's assume that z is an eigenvector, then v prime is equal to 3 times z is also a solution because 3 is there on the left hand side, 3 is on the right hand side. Right. So if z is an eigenvector, that means a times z is equal to lambda times z. It's z prime, so now a times z prime is equal to a times 3 times z. Pull out the 3, so that's 3 times a times z, that's equal to 3 times lambda z, because that's true, and that's the same as lambda times z prime. Right? That's also true. There is nothing special about this tree. I could have chosen 3 to be 4, 3 to be 5, for that matter, any number. So if one eigenvector is a solution, I can multiply that in scale. If z is a solution, double it, that's also a solution, triple it, that's also a solution, -1, -2, all those are solutions. So the whole line, so it's a direction that is an eigenvector, typically, or at least if you normalize it, that's an eigenvector. Notice normalization is coming in. So we are, as I said earlier, that we are building this. We did this last time, and now we are asking what's the easy way of getting this? How can we get them? That's just by taking a matrix and getting these eigenvectors are nothing but those spaces vector, and they will come out as orthonormal most of it. Anyway, so, so let's take lambda equal to e raised to plus I theta, and let's ask what our z is. We are asking what is z. So put this in this equation here. So we have cosine theta minus lambda, which is e raised to I theta, that is sine theta, minus sine theta, and cosine theta minus e raised to I theta. And we are asking what is z1 and what is z2. That's what we're looking for. And cosine theta minus exponential of I theta, the cosine theta cancels out. So what I have left is a minus I sine theta. It's minus I sine theta. Sine theta can be pulled out, probably. So let's see the lessons. Sine theta minus sine theta and minus I sine theta. So apparently sine theta can be pulled out. One, two, 0, 0. Let me actually pull that out. 0 minus 1 minus 5. Again, our goal was to find sine theta. It seems like, our goal was to find z1 and z2. So it seems like it will be independent of sine theta. Something multiplied by this gives you 0. And if it is there on both terms, that doesn't contribute. So we have minus I times z1 plus 1 plus z2 is equal to 0. And it immediately tells us that z2 is equal to I times z1. And that immediately tells us the solutions. For example, if z1 is, I choose z1 to be 1, so that's so z will be equal to z1 is 1, then z2 is I, right? That's the solution. If I choose z1 to be 2, then it is 2 times I. Right? These are all solutions. I can choose half. So if this was half, so that's half and I by 2. As I said earlier, these are all many solutions associated with that. So this is like a vector that you keep multiplying that vector with something. There are many solutions. So immediately you say that, oh, we should put a condition on it that it is normalized. I want that particular vector out of this, which has a unit length. Right? So I put an additional condition that z1 squared plus z2 squared is equal to 1. Is that a normalization condition? The small catch to that.
It's not visible anymore. Getting smaller.
Yes, what?
It's getting smaller and smaller.
Oh, it's getting smaller. Bigger and bigger. Or I should go that side. Right? I should come this side. Yeah, let's come this side. Let's keep this and okay. That's the basis. Okay, so I said we have minus I z1 plus z2 is equal to 0. That implies z2 is equal to I times z1. Slightly bigger.
Yeah.
No,
Still small. Okay.
what happened?
We-
Earlier, I was
Maybe we can ask him.
Niranjan, how is it? Okay, right, a little bigger, easy.
It is readable.
It's blurry.
little bit.
Little bit, okay. Minus I. Better? Or is it still?
Yeah, when
better?
you write, yeah,
Just focus it a little bit to the front. Maybe make it, so this is, I mean, content here maybe. Move it to the left a little. That's it. Okay. Yeah, now zoom in a little more. More. Yeah, now make it a little top. Yeah. This should be okay, right?
that's better.
Yeah, weird. Well, it's zooming in somewhere else, I think, or it's focusing somewhere else. Is it when I am standing that it is focusing on my face? There is an autofocus?
Yeah, I can see you clearly.
No, is there an autofocus feature that when I am in the frame, it is worse, and when I'm outside the frame, it is better? Like there are these features where we focus, right?
Or yeah.
Is there any such thing?
Ah, yeah.
Right?
Yeah. It's blurred.
What do I do? I cannot stay out of the frame. That's simple solutions. All right. Okay. Huh? Turn it off.
And autofocus.
I don't know where it is. Do you know? Yeah, I don't know. Yeah, so that should be yeah, that's what we should do, but I'm pretty sure we'll get distracted. It might be a 15-minute project. So, yeah, so let's survive like this, Niranjan. Okay.
Yeah. If you write that big, it is clear, I believe.
Okay, I'll write that page. Yeah.
I know you prefer to write a little smaller.
It's a tendency. Yeah, I prefer. Yeah. Yeah, I'll do this. Yeah. Okay, I can. So Z2 is equal to I times Z1. And then we look for what are the solutions. We said Z is equal to, if I put Z equal to 1, because this Z1 is equal to 1, then Z2 is equal to I, right? That's basically 1 and I. Other solution is if I put Z1 equal to 2, so then it's 2 times I. Oh, I got smaller very quickly. Huh? Okay, now I'll get bigger. 3 times I, and so on. But then we say that, oh, all that doesn't capture everything. It is only the unit vector that is important. So let's put an additional condition. That's Z1 square plus Z2 square is equal to 1. And I say that is not sufficient to say that it is normalized. What's wrong in that? It is an absolute value, right? But since it's complex numbers, we have to say the length of this vector is decided by the absolute value of that, right? So that has to be equal to 1. So this is an additional condition, or it's a normalization condition. But it's not necessary for it to be an eigenvector, not necessary for it to be an eigenvector. So we are asking now, we are not just looking for an eigenvector, we are looking for a normalized eigenvector. A one vector which is very special, which has a unit length. There are many eigenvectors. There is a multitude of them, infinite of them. So we picked one of them which has a unit length associated with. Then we have a little more freedom here, or we can actually, earlier there was only one condition we got, right? So that maybe I should ask, so that is one condition, but we used only one of the equations. What about the second equation? So I can use the second equation and make it precise, right? Z1 and Z2, I said it's not the same. So why did I not use that? If I have two equations, then there is no freedom. Right? Why did I not use that? Is the question clear?
The second one gives us another set of
No, there are two equations, right? So there is two equations there. So minus I Z1 plus Z2 is equal to 0. The other one is minus Z1 minus I Z2 is equal to 2, 0. If I solve a linear set of equations, I'll get a unique solution, right? But I'm saying it's not unique. I didn't even bother to use the second equation, and then I said that it's not unique. Why did I do that? I say I'm wrong.
We have two eigenvalues and two eigenvectors.
That's correct, but we are now in first eigenvector, right? So lambda is fixed. So everything we are doing is for one eigenvector. This whole thing will be repeated for the second one. That's correct. But for that first eigenvector, I have to solve for Z1 and Z2, right? That's my eigenvectors. Or for that eigenvalue, I have to get the eigenvector. And in that process, I get a linear set of equations. If I have two equations and two unknowns, I can solve for the two unknowns. But even before I try to attempt that, I said, oh, I got this, I'm not even going to attempt that. Okay, why did I not attempt it? Very similar. What do you mean by similar? Maybe more? Better?
Second equation.
Exactly. This is not a new equation at all. Right?
That sense.
So this is identical. Like if I multiply by an I get that. So this is not even a new equation. First of all, there is zeros on the right side, right? That's a bigger problem. Right? So, but even otherwise, this is not independent equations at all. And always that is the case. In the eigenvalue problem, the second equation is never independent compared to the first one. They will always be related. Right? If I multiply by an I get this. Right? I square is plus 1. So it is the same. So I didn't even go and proceed with that. So that's the multiplicity that we are getting. And then we are introducing an additional condition that is a normalization condition just for convenience. It is not a property of an eigenvector. Okay. So with that, then I have two conditions now. So now this is a condition for the eigenvector, and this is for normalization, additional condition not coming from those equations. Nevertheless, I can now solve for Z1 and Z2. So Z1, let's solve for Z. So Z1 magnitude square plus Z2 is I magnitude is again Z1, right? So this is Z1 I times Z1 square is equal to 1. I square is magnitude wise, it is 1. So it is 2 times magnitude. Oh, I got again smaller. This big, this 2 times Z1 square is equal to 1. And that gives me magnitude of Z1 is equal to 1 over root 2. That's only the magnitude, right? I still have some freedom there. That complex number, if you fix the magnitude in a complex plane, that is a whole freedom of going around in a circle, correct? So this implies that Z1 is equal to 1 over root 2, and then I can multiply by face. This is equal to I times alpha 1 times root 2. When alpha 1 is a completely arbitrary face. Alpha 1, alpha 1 is an arbitrary and I should again emphasize that we are looking for an eigenvector. That eigenvector is, we said, not unique. It only has to satisfy that. But even after that uniqueness has been taken care of by the normalization condition, I still have an arbitrariness in the eigenvector, and that is given by a face e raised to I alpha 1, but that can always come out. I can always multiply that out. So now notice what is my z corresponding to the first eigenvector. That's z1 and z2. That's z1 and z2 equal to z1 is e raised to I alpha 1 over root 2. And the second one is z2 is I times that. So this is I times e raised to I alpha 1 over root 2. That's equal to, first of all, that is a face e raised to I alpha 1 over root 2, and that is 1 and I.
Can you please move the camera to move it down?
Oh, camera.
Thank you.
If I had put an arbitrary number here, which is not necessarily having a magnitude of 1, that's what the property of an eigenvector is. But this is a normalized eigenvector. Even in that normalization, there is a phase independence. Most of the time in quantum mechanics, this is not important. We cannot observe this, and it never comes out important unless you're very clever. Something comes up, like examples are monopole, Berry phase. So there are some non-trivial features sometimes we associate with it, but most of the time we will not be keeping this. Like you can say that, okay, I'll pick one outcome. So you can choose alpha 1 equal to 0, for example. So, but in general, there is an arbitrariness, and anytime there is an arbitrariness in physics, remember, you cannot have it, because experimentally you do some measurements, you cannot. Oh, we're not shocking. Plug it on this side. Okay. Is it charging now or is it?
Yes.
Plugged in? Good. So an eigenvector has an arbitrariness of a coefficient in general, and even if I normalize it, there is an arbitrariness associated with a phase. And in physics, whenever you associate with a measurement, you cannot have an arbitrariness, because a measurement does not know what alpha you chose if there is an arbitrariness. So if it is there, somehow you have to either at an interpretation level, at a postulate level, you have to say that why this is not the case. Usually these are places where you look for something must be missing. There must be some fundamental reason why there is this is not there. But we are, as of now, I have not introduced anything. This is just a matrix, and a matrix has an eigen vector, and an eigenvector has an arbitrariness in a phase even after you normalize. Right? Just saying that this should be equal to 1 is not sufficient, because even an exponential of a I times a constant is 1, so you're still left out with that argument. In our case, whenever necessary, we will put this equal to 1, but that's not necessarily the most convenient or most correct thing to do. Maybe that's a way. Every time there is an arbitrariness, that's not good. So that means you can have any answer you want in principle, right? So that's not okay. Okay, so that's your first eigenvector. Sometimes we will call this E1. This can be E1 in our earlier way or notation of having a vector, but this E is the same as this. This is exponential of the value of exponent 2.7 or something like that. So this is just a symbol for our vector. So that's your eigenvector. Any question here, especially with this step? This is the only thing that you should not be familiar with, otherwise you must have done this somewhere or the other. Any comments or anything?
Dr. Sajesh, that arbitrariness came into there because when we have two variables, we don't have two different equations. Is that the reason?
Yeah, so okay, maybe if I make it a little new point this here. Yeah, okay, notice this was the only one equation we got. Now, for taking that arbitrariness off, I said I'll put an additional condition here. But this additional condition still does not take away the complete arbitrariness, because that's because Z1 and Z2, that is X1, X2, so X1 plus I X2 or Y2, let's say Y1, right? And X2 plus I Y2, right? Since these are complex numbers, there are 4 unknowns. Right, out of those 4 unknowns, this equation has 2 of them because this is a complex number equation. These are 2 equations. So this is 4 minus 2. Can you read this? By the way, I wrote it small.
Yeah, I can read it.
Right. So these are the 2 complex numbers, Z1 and Z2. 4 unknowns. These are 2 equations because it's a complex number equation. So that's still I have 2 unknowns. This is the third equation. This is a real number equation. So put this 1 minus 1. Say I still have that arbitrariness of 1 variable. And that's that angle theta that is showing up. If I want to solve for 4 unknowns, I need 4 equations.
That's right.
And I have only 2 equations here. I added 1 by saying normalization condition. But that still doesn't take away the whole thing, because in a complex world, normalization doesn't mean just one value, it's a whole circle of points, right? That's a phase.
Yeah.
So that circle, that phase is what is showing up in the last line here that we showed. Okay, that's that phase of that complex plane. Does that help?
Yeah. Thank you.
Okay. And the best way to see is that whatever we construct from here, it better be independent of this fix. Like in electromagnetism, we have this feature of gauge transformation. And that is like all the physics that we do, it is dependent on the electric and magnetic field. But electric field and magnetic field is built out of potentials and vector potential, scalar and vector potential. They are gradient and time derivative of each other. Like electric field is got by the gradient of that. But a gradient always will take away a constant. So there is an arbitrariness in that. And that's called the gauge arbitrariness in electromagnetism. Now you can say that, oh, that's not there. Always we measure electric and magnetic field. As far as you're working in things with electric and magnetic field, you're good. But you can always get clever and say that I'm going to build a configuration which actually is sensitive to this constant that is getting negated. And that's the whole idea of what you have heard of Aharonov-Bohm effect, right? It's a very interesting phenomena, which quiz, right? that advantage of this. Let's say I don't know. Bones effect. And I mean, the idea is very simple. Let's say, okay, yeah, let me tell this digression, but now let's okay this. So let's say we have a solenoid. This is a solenoid. A solenoid is a cylindrical coil. All of us familiar with a cylindrical coil, and that's a solenoid. What is the magnetic field associated with the solenoid? Formula? Mu naught M mu I M. N. Yeah, N. Yeah, that's correct. So there is a constant mu naught, right? Then there is a current that goes through. And you can say number of turns per unit length. So number of turns per unit length of the solenoid, right? Mu naught a constant, current that goes in a coil, and number of turns per unit length. The length is the length of the coil that is going into the board, which is infinitely long, preferably, or very long. So this is the number of turns. Both are infinity, but number of turns per length. The density of the turns is what decides. What is the magnetic field here? Like this is the magnetic field inside the solenoid. What about outside? So outside is 0, right? So that's 0. This is outside. And this is inside. If you notice, this should be very when first time someone tells you, I mean, we study this in textbooks all the time, but first time when you told, when you were taught this, it should bother you that it does not depend on the radius of the solenoid. Whether I make the solenoid 1 meter wide or 1 centimeter wide, it doesn't care. Right? How come it doesn't depend on the radius of the solenoid? But you can check this. So you should have bothered you, and you should have gone and said that, no, I don't trust this textbook result. So one should rederive it. But how much ever you derive it, it seems like it is correct. It is independent of the radius of the solid. Where else do you see something so drastic that is independent of the geometry of the object itself? It's right there around us. The gravitational field that is experienced by Earth doesn't depend on the radius of Earth. Like if you're on the International Space Station and if you don't see Earth, there is no way it depends on the radius of Earth, right? It only depends on the center. You notice there's Earth here, there is a radius R, and let's say that's the International Space Station. That's not that far away, it's 400 kilometers, that's somewhere here. That's your radius R. The gravitational field at that point is independent of R. It only depends on the center to that point. If I were to magically compress the Earth a little bit of the radius, what will happen to the International Space Station? Nothing. It will go the same way. I can keep compressing this, keep compressing it, and make it a black hole. Like black hole is a very, when it crosses a threshold, there is a very special radius. When you cross that, that planet or an object is called a black hole. If I were to compress this Earth small enough to make it a black hole, what will happen to the International Space Station? Nothing. It will still go in the same way, and it will be oblivious to the fact that there is a black hole there. It will just know that there is a mass there, but it will not get affected. There is a black hole at the center of our galaxy. It's an understanding. We don't see it, but we see the effects of it. But we keep going around in circles, right? We don't just get sucked in just because there is a black hole. And I mean it, that you can do the calculation, go and read about it. You can compress it as much as you want because it's independent of the radius of the Earth. Okay. So anyway, so with that counterintuitive feature, that's the same thing with a solenoid. It doesn't depend on the radius A, and whenever there is something that's independent of, do whatever you want with it. And make something non-trivial, that make it small. Make the solenoid very thin, and you have a thin filament of wire, which has a magnetic field only inside. You're having a world where there is magnetic field zero everywhere, except for a very thin filament of wire inside which there is a magnetic field. So you've basically confined a magnetic field. So let's make that. So we have as such a solenoid, that's a small solenoid. It doesn't really matter whether it's small or not. And there's a magnetic field, let's say, that's coming out of the board, right? So that's your P. Again, I got small. Can you read that? No. Cannot. Okay, make it bigger. That's a zoomed in picture. That's your magnetic field inside that solenoid. If you have a magnetic field, let's say that's a magnetic field coming out of the board. If you have a positive charge moving with velocity v, what's the force it experiences?
QV cross B.
QV cross B, right? That's the Lorentz force. What is the force it will experience here? A positive charge moving with velocity v, charge q. What's the force it will experience? At this point, the magnetic field is there inside that solenoid.
QE.
QE, because it's not changing with time. Uniform magnetic field. Why did you say QE? Electric field?
Oh, but there is no
There
force
is-
from
there is
magnetic
no-
field.
Yeah, that's the question. Will there be a force from the magnetic field? There will not be, because the magnetic field is inside, right? When you say Q times electric field, it is electric field at the position of the charge. Not, it is local always. Right? I experience the gravitational field here, not the gravitational field in the International Space Station. Right? It is my position that decides what gravity I'll experience. So this will be decided by the magnetic field at this point, which is zero, because the magnetic field is all confined inside that solid. So this is free in a sense. No force it is experiencing. So now let's, this is the experiment, Aharonov-Bohm effect. It should start from here. You go around this, no experience, you're just basically an electron is moving around, and it does this, and you send a beam of electrons. You send a lot of beam of electrons this way. Basically, it can go either to the right or to the left, and you see a pattern here. These lines that you see, dark and white line. If it was really random, there was no effect from the magnetic field. It should have all been just randomly distributed there. But you can explain this by showing that if you go around a magnetic field once, it gets notice. It somehow knows how many times it is going around the magnetic field. And then you bring in the idea. So how do you explain this? Even though there is no magnetic field, what is there in it is magnetic field is given by an electric potential, which is the curl of the vector potential. Is that familiar? Right? So exactly like electric field depends on the electric potential, gradient of the potential, and you say that potential should not be observable, like it is always, you can subtract out, right? There is a ground in electrical circuits, you will ground it, but you never know whether that ground is there or not. Independent of the ground, your observations will not change. It's always plus or minus, right? Whether if you change the ground to +3 volt, that doesn't matter. You're just changing your origin. So that doesn't matter. The same thing is a more sophisticated version than the potential. The magnetic potential is A. Now the idea is that the magnetic field is confined within this potential and within the solenoid, but the vector potential is not confined. There is a vector potential here, which affects the charge, but vector potential doesn't affect it in a very classic sense. The only way it can affect it is when you go around completely. So that's a non-trivial way of a quantity that you think is never observed. So A is never observed. That is true. I'm not trying to say that A can be observed. But what you can observe is a loop integral of A. So an electric potential still cannot be observed, but there are some small features of it that can be observed experimentally. And in this case, it is the loop integral of A dotted with dl that can be observed. And somehow the electron going around the magnetic field captures that. And that's what this experiment did. The whole point here was that whenever there is an arbitrariness, first of all, you say that, yeah, that physics should be independent of arbitrariness. But then if you get very clever, sometimes you can use those arbitrariness to come up with very counterintuitive experimental results. Right? And this is a result of that kind. Complete digression. Here the only way to motivate this was that particular example. Okay. Any comments or questions on that? Okay, so let's go. Niranjan, question?
No, I'm good.
Where is this? Okay. Oh, I erased everything. Let's summarize it. So we had our matrix A as cosine theta, sine theta, minus sine theta, cosine theta. We got our eigenvalues as lambda is equal to e raised to I theta and e raised to minus I theta. Corresponding to the first eigenvector, we got the eigenvalue, we got our eigenvector as there is an arbitrariness, which is e raised to theta 1, let's say, and then there is a 1 over root 2, that's for normalization. And what was this? 1 and then I. Right. That's what. And we said this is also going to be, we will use the symbol, right? This is, we will start using this, at least some. That's a connection we wanted. If I were to have lambda equal to exponential of minus I theta, I get, help me. Let me quickly do this, right? So cosine theta minus, so it is I sine theta plus sine theta, and then this is minus sine theta and I sine theta, that is equal to 0. V1, V2 is equal to 0. That means I times Z1 plus Z2 is equal to 0. This is readable. And Z2 this time is equal to minus I times Z1. I still use the normalization condition. That is all I can do. I cannot do more than that, but now we use normalization condition. Z1 squared plus Z2 squared is equal to 1. Same idea, minus 1 goes away. So V1 must be magnitude of Z1 must be magnitude of Z2. So magnitude of Z2. No, Z2 I'm replacing, so I get Z1. Sorry. I'm solving for Z1 and then Z2 is away. Yeah, Z1 is equal to 1 over 2. Right? So Z1 is equal to e raised to I theta 2 over root square root of 2 theta 2. Second arbitrary constant. First one was arbitrary here already. This is the second arbitrary constant. Once I have Z1, then this is minus I. So Z will be equal to e raised to I theta 2. Another arbitrary constant, 1 over root 2 times again 1. And this is minus I. And we will show that. I was really wanting to do a lot more. Okay, we'll stop here, I suppose. I want to do next time at least, I want to do polymatrices. Basically, these are simple matrices. They're standard matrices. We will call them a name, and at least in your homework, you will see these are polymatrices. That's it. We won't talk much more than that. 0, 1, 1, 0. Sigma cubed 0 minus I 0, and sigma 3 is going to be 1, 0. But what will be interesting is that now, okay, what are we doing here? Let me give you an idea of. I said first that given a matrix, I can build eigenvectors out of it. I will not motivate where this polymatrices come by. But for our information, these are 3 matrices that are suitable for representing the spin of a particle, the electron spin, if you want, or angular momentum in general. That's a convenient thing. We have 3 operators now. That means we have 3 bases. I have 3 matrices, I have 3 bases. At least we have 3 bases. We will build infinite bases almost immediately. But now we have 3 bases, and that's what we will talk. Now we allow in matrices E1, G1, and H1 like that. 3 bases, and then what can we do with it? First, we do an experiment with 1 basis, change the basis. How will the experiments look like? Then again change the basis. How will we look like? That will be the effect that we'll talk about. And yeah, probably it will go for 3 lectures maybe, and then we'll. That is a homework that should be straightforward. You should be able to do it tonight itself. I was almost thinking of making it due on Monday, but then I thought I would give you more time. Okay.
What about this one? Can we submit on Monday or due today?
Which one this due?
Due today.
Try to make it knowing you. If I tell that it is due today, you'll finish it today.
No, I'm trying my
I had the
best.
same question that I was at the presentation today, so I couldn't work on this.
Yeah, then make it. Yeah, make it Monday.
Monday?
I mean, both of them on Monday.
Yeah, make it fun. Yeah. So the
Thank you.
homework has been on popular choice, postponed to Monday, but finish it off. Next homework is still due on Friday. So I say finish it off. If you can finish it off, they have some other priorities in life. So they want to finish it, but that's okay.
Thank you, Sanjay.
Oh, yeah, Niranjan, yeah, thank you.
Yep, see you next time.
Yeah, thanks. Yeah, thank you. Nathan, how's it going?